All right, so we've got a lovely topic called roots of unity. And what I want to do is give a couple examples before I talk about a few things in general. And then there's a really nice conclusion at the end where we figure out something about what they all need to add up to equal. So before I get to that, the word roots of unity means we're looking for solutions of the equation that is equal to 1. So we have a certain power and we're trying to find all the solutions that make the number to that power equal 1. So I'll start with the simple example of z squared equals 1. Many of you have learned, okay, you take the square root of both sides and you get z equals plus or minus 1. Okay, those are the two roots of unity. The word unity just means 1. Roots because we're taking the square root. If I think about those as complex numbers, it turns out I could think of them as the number e to the 0 and e to the pi I. And where did I get 0 and pi? I'm visualizing that this is a 0 degree angle pointing due east, so that's the number 1. And then this is a pi radian angle. It's 180 degrees, so it's pointing due west. So 1 and -1 right there. Let's look at another example. Let's look at z to the third is equal to 1. One of the answers is easy and the other ones are not. It's pretty clear that if you raise 1 to any power, number 1 raised to any power, it's just going to equal 1 again. So we know that we're always going to get the number 1 as one of our roots of unity. But it turns out when you go through the process here, there are two other answers that also work. And so here's how I think of it. Z can be written as RE to the I theta. Here, I know that R has to be 1 because I am one step away from the origin on my target number, meaning this number has a radius of 1, therefore this number also needs to have a radius of 1. So really what I'm thinking about is e to the I theta cubed has to equal 1. Well, let's express 1 as e to the I theta. It's a 0 degree angle. But really, 1 is not only a 0 degree angle. 1 is also an angle of 360 degrees and 720 degrees and -360 and all those different multiples, 3,600 degrees. Any multiple of 360 degrees is also equal to 1. When we did the second power problem, we got two answers. So when we do the third power problem, we expect there to be three different answers. So I think of this as there are three possibilities. It's equal to e to the I times 0, e to the I times 2 pi, or e to the I times 4 pi. I don't need to go beyond 4 pi because then I'm just looping back around to get more than three answers. So there's going to be repetitions. So what that means is that there's actually three different possibilities for theta. It's 0 divided by 3, or theta is 2 pi divided by 3, or theta is 4 pi divided by 3. And that leaves me with a complex number right about here and right about here. This is 2 pi over 3. This is 4 pi over 3. If I write them as e to the I times 2 pi over 3 and e to the I times 4 pi over 3, that's okay. That's writing them in Euler's form. But it's kind of nice that you can actually extract, by thinking of cosine and sine, you can actually extract the Cartesian form. It would have been hard to come up with these complex numbers. Oops, I should say minus on the bottom there. It would have been hard to come up with these complex numbers directly. You would have had to think, what a plus bi to the third power equals 1? And you'd have to expand out a plus bi to the third power. Like, you could do it if you go a plus bi to the third power. You'll just get a cubed plus 3a squared bi plus 3a bi squared plus bi cubed. And you can do that, and you can figure out when that equals 1, and it turns out that these are the three different answers. It's just a lot simpler to do it in Euler's form. So we have three answers, and they all sit on that unit circle, just like these ones sit on the unit circle. And these two answers are 180 degrees away from each other. And these three answers are 120 degrees away from each other. So it's 120 degrees there, and there, and there, because that's a third of a circle each time. And the reason it's a third of a circle is because we took and divided by 3. We divided a full circle by 3 every time. And if we did 6 pi over 3, which would have been our next answer, we would just end up back here at 2 pi anyway. So that's the big idea about roots of unity. They are all the solutions to the equation z to some power equals 1, and they are equally spaced around the circle. And there's another really nice fact about them. What I want you to notice is that if you add up our roots of unity here, what number do you get? If you add up our roots of unity right here, what number do you get? The conjugates are going to cancel each other out. So then you just have negative 1/2 and negative 1/2 and positive 1. That makes 0. Negative 1 and positive 1. That makes 0. Okay. In fact, this is a general truth about roots of unity that if you add up all of the roots of unity, you're going to end up getting 0. Another thing that's sort of surprising about roots of unity is that one of the roots of unity can generate all the rest of them. If you look at z equals negative 1, and if I square negative 1, then I get positive 1. If I multiply by negative 1 again, I get negative 1. So there is a cycle happening where if you raise powers of a root of unity, you're going to get all the rest of the roots of unity. If you look at the other example here, where if we look at this one right here, e to the 2 pi over 3i, if we square that, it means doubling the power, so we have 4 pi over 3, times by itself again, so we add another 2 pi, that's 6 pi over 3. Add another 2 pi, that gets you right back here. And so we have this cyclic nature, where the first root of unity that's not 1 can generate all the rest of them by raising it to powers. So I'm going to take those two facts and prove the general statement that the roots of unity always sum up to equal 1. So let's look at an example in general. If I start with the equation z to the n is equal to 1, I'm going to get n different solutions. And the first solution that's not equal to 1 is going to be written like this. This is just the first solution, so I'll put a little 1 right there. It's going to be 2 pi over n e raised to that times I. So now what my claim is that I could get any solution by raising that to whatever power I want. So if I want the first solution, I raise it to the first power. If I want the 0th solution, I raise it to the 0 power, and that would just equal 1. If I want the nth solution, I would just raise it to the nth power. Okay. Now the nth solution is the same as the 0th solution. So using these ideas here, because this is just really saying it's e to the 2 pi k over ni, which is what we just saw previously, I can come up with a wonderful factorization. I hope you agree that z to the n equals 1 is the same as z to the n minus 1 equals 0. And I hope you also agree that I can factor that as z minus 1 times z to the n minus 1 plus z to the n minus 2 plus etc. all the way down to plus 1. Just imagine distributing it out. If you multiply by z, you're going to get all of the powers added by 1. And if you do minus 1, you're going to take away all those terms except for the last one, and that's why you get z to the nth minus 1. So I'm going to return to this idea. A lot of people say omega. It's okay to say w as well. You're just saying, let's look at a solution that's not equal to 1. And why is it important to look at a solution that's not equal to 1? Well, our original equation is equal to 0. So our factored equation is also equal to 0. And when you factor something, that means there's two possibilities. Either this first chunk equals 0, or this second chunk equals 0. We claim that our W value is not 1, but it is still a solution of the complex number. We also claim that the first solution can generate all the other solutions by raising it to powers. So what I can tell you now is that this chunk right here represents all of the roots of unity. Here is the 0th root or the nth root. Then the first root would be right here, z to the first. This is the n minus 2th root. This is the n minus 1th root. All of the solutions, all of the roots of unity are right there. And guess what they all sum up to? They all equal 0. The sum of the roots of unity is equal to 0. Now, this gives you something a little bit surprising. Remember that we can break apart our complex numbers into cosines and sines. So if I look at my W as e to the 2 pi over ni, I can actually write that as cosine of 2 pi over n plus I sine of 2 pi over n. And I know that the sum of the roots of unity is equal to 0. So what I know now is that if I take all of these iterations, I can come up with equations that have to be true about cosine and about sine. Okay? So for example, let's just look at an example of like say n is equal to 5. Okay? Then what I'm going to have is I'm going to be able to say z to the n minus 1, so that means z to the 4th. So I'll have cosine of 8 pi over n, I multiplied by 4, plus cosine of 6 pi over n, multiplied by 3, cosine of 4 pi over n, plus cosine of 2 pi over n. Oh, I'm sorry. I should say over 5. My n is equal to 5. There we go. I knew something was wrong. Okay. Plus 1 has to equal 0. And that's totally a not obvious fact. Why would you expect that to equal 0? Well, it turns out to equal 0 because we know the sum of all the roots of unity is also equal to 0. And similarly, I know that sine of 8 pi over 5 plus sine of 6 pi over 5, etc., also has to equal 0. So that's kind of neat. So roots of unity just mean all the solutions to z to the n is equal to 1. There's always n solutions. They're equally spaced around the unit circle. And the sum of the roots of unity always has to equal 1. So there you go. Let me know what was confusing, and I will help out.